Hi guys, welcome to Netgate Chemistry. So till now we have discussed about particle in a 1D box, and now in this video we are going to discuss about the particle in a two-dimensional box. So first of all we have to consider a two-dimensional box. So suppose we are having a two-dimensional box, and this is along the x-axis, the length is 0 to Lx, and along the y-axis the length is 0 to Ly. So this is the two-dimensional box, and inside the box particle can move, will be having potential of 0, right? And elsewhere outside this box, anywhere it is going to have potential of infinity outside this box, right? So basically when we are talking about this particle in a 1D box, so if we talk about the potential values, so it is going to be 0 when particle is between 0 to Lx, also 0 when particle is between 0 to Ly, and infinity when it is elsewhere, right? So these will be the potentials. Now if we want to write down the Schrodinger wave equation in this two-dimensional, that will be del square psi by del x square plus del square psi by del y square plus 2m by h cross square e minus v into psi equals 0, right? Also in this equation the energy E will be equal to Ex plus Ey, right? Because energy is an extensive property. Also the wave function psi is going to be the multiplication of psi x and psi y. These two things are really important for us. Okay, so this will be the case. So now first we are talking about particle inside the box. So inside the box potential is 0. So now in this equation if we substitute these two values and potential equals to 0, then what we are going to get is so basically what I have done is I have substituted these two values and v equals to 0 in this equation. I have got this equation, right? Now moving further, now here we have del square by del x square. So del x, so psi x will act as variable and psi y will be the constant. Similarly here psi y will be the variable and psi x will be the constant. So here psi y will move out, here psi x will move out, and after that what we are going to do, we are going to divide the whole equation by psi x into psi y, right? So divide the equation by psi x into psi y. Remember here it is going to get multiplied by psi x, psi y will remain outside. Here it will be multiplied by psi y and psi x will be outside because it is a derivative, right? Derivative of x and derivative of y, partial differentiation, right? So now after doing these two things, what you are going to get is So this is what you will get, and after this what you have to do is, here 1 upon psi x del square psi x by del x square plus 2m ex by h cross square equals 0. That means del square psi x by del x square plus 2m ex by h cross square psi x is equals to 0. That is, here I have multiplied this whole equation by psi x, and now after this you can find out the value of psi x, which will be root under 2 by lx sine of nx pi into x by lx, and here ex is going to be equal to nx square h square by 8m lx square. Now similarly you can find the value of psi y, which will be 2 upon ly root under sine of n y pi y l y. Similarly ey, I am writing down here, ey will be equal to n y square h square by 8m l y square. So basically these are the things which are important for us, right? So if you are not able to do these derivation part, so don't worry about it. You should know the Schrodinger wave equation, these two things, right? Inside the box potential is 0, and these things you should know. These things, why I have done this, so that you could understand how we have came across these things, right? Now psi is equals to psi x into psi y, and e is equals to ex plus ey. Remember that. So if we want to find out the overall energy, then that is going to be equal to ex plus ey, that is summation of these two values. So that is going to be equal to nx square h square by 8m lx square plus nx square ny square h square by 8ml y square. This will be the overall energy, and this is the case when we have two-dimensional box in which lx and ly, right, length along x and y axis are different. But what if lx and ly are going to be equal? That means if the box is symmetrical, that is, instead of rectangle, here we have a square, right? Here we have a square. So this length is also 0 to L, and this length is also 0 to L. In that case, Lx and Ly both will be replaced by L, and overall energy will be E is equals to nx square plus ny square into h square by 8 ml square. So this is a very important conclusion which you have to remember always. So basically most of the times we get particle in two-dimension box whose length, this length and this length are basically equal. In that case we are going to use this formula of energy, right? So this is the case, and now I want to give you one homework. That is, what you have to do is you have to find out the degeneracy of each energy state and also the value of energy of each energy state, just like the case we plotted for the particle in a one-dimensional box. You have to plot the values of each energy state and the degeneracy values. So you have to do this as a homework. So what you have to do is basically, just like in the previous case, you have to plot the energy values for n is equals to 1, for n is equals to 2, and so on. Also you will find some degeneracy values when you are going to put these nx and ny values differently. So you have to find out the g values for them as well. So we are going to discuss that part also, but you need to do that by yourself for once, right? So after that, in the next video we are going to discuss about particle in a three-dimensional box. Now these things are going to be very easy because we have understood particle in a 1D box very effectively. And after doing particle in a three-dimensional box, we are going to move further with hydrogenic atoms, that is hydrogen atom. So that is a main part which you have to understand very wisely. So we'll move on to that. So till now we have not finished the first chapter, so with that we will be very close to finishing the first chapter after finishing the hydrogen atom. The second chapter which we are going to study after this, that will be having the perturbations and all. That is, in the first chapter we study all the ideal cases, and in the second chapter we study the perturbations. So we are going to study that part as well in the second chapter, but first we are going to move ahead with the particle in a three-dimensional box. So far that's it for this video. Thank you so much for watching.